Today we are going to investigate 3 different methods of vector addition in 2 dimensions. Experimental, the force table, graphical, with paper, ruler, protractor, and then mathematical. The 3 methods are interrelated, but they can be treated independently. What we want to do in this experiment is treat the 3 methods independently and then compare the results from the 3 different methods. We should get the same result, but there's going to be experimental errors with the force table, human error, I guess you could call it, with the graphing. I mean, we can only draw lines, measure their angles and lengths, etc. with so much accuracy. Now, the purpose of this introduction is to show the interrelationships between the 3 methods, but I want you to bear in mind when you're doing the experiment to treat the 3 methods independently. So don't borrow results from one method to the other, because that'll ruin the process of comparing the 3 results at the end. I'm going to start by talking about graphing. Now, some of you may be familiar with navigation. We're north, south, west, and east. Now, in navigation, now I'm sure you're all familiar with those compass directions. In navigation, however, if they want to know detailed directions, they say that north is equivalent to 0 degrees direction, east is equivalent to 90 degrees, south is equivalent to 180 degrees, west is equivalent to 270 degrees. And then you can see how you can get any direction in between by specifying a number of degrees or even fractions of degrees. So unlimited precision. We should be careful to call these orientations and not degrees. Notice how these orientations increase clockwise. The reason I'm showing you this is because a lot of students look at these force tables and they might know a little bit about navigation and they can't resist saying, well, the 0 must be north and the 180 must be south, etc. We are going to use the mathematical definition of orientations, not the navigational or astronomical definition, which is what this is. Okay, so 2 major differences. So instead of talking about north, south, east, and west, it's related to that, we talk about the familiar x minus x and y minus y. But x is not 90 degrees. Okay, so in the mathematical definitions of orientations, x, positive x, is a 0 degree direction. Positive y is 90 degrees. Negative x is 180 degrees. And negative y is 270 degrees. So 360 degrees with that positive x. So not only are these numbers different up, down, left, and right, but it increases counterclockwise. Okay, so you absolutely, when you're using these force tables, you don't want to think about north, south, east, like that, you want to think about x and y, and negative x and negative y. What I'm going to do to demonstrate the connection between these three different methods is I'm going to do an example. First I'll set it up on the force table, and then I'll show what it looks like graphically, and then I'll show you how the math can come from the graphing. In this example, we'll add two vectors. We're going to call them A and B. So A vector is going to be 120 grams. And by the way, here I'm using grams as substitute units for newtons. And the reason for that is so that I don't have to keep converting from grams to newtons and then newtons back to grams. It makes us quicker, and it also avoids the error. One thing you got to keep in mind though is that with what we're going to do today, we're only involving forces, so force vectors, and we're not calculating anything from those forces. If we were wanting to calculate various quantities from these forces, so for example, acceleration, torque, energy, moment of inertia, things like that, we would have to make sure that we convert our gram unit into newtons. What we mean by a force being a certain amount of grams is that it's the force of gravity in grams. And what we do is so 120 grams is I'm going to hang 120 grams. You got to be careful to include the mass hanger, which is 50 grams. So I got 50 plus another 50 plus 20. It's 120 in total. You hang that from a string. Now that generates a tension in the string. The string goes through the pulley, and then it pulls on this ring. So each of these strings is going to pull on the ring. The way this works is that strings, when they're stretched, they pull in from the end. It's just like if I had two people pulling my arms, and they wouldn't even have to pull them the same amount, but they're pulling in opposite directions. I am going to be stretched, and the way I react is I react by pulling back in. That's what this string does here. So each of these strings, they're pulling back in. So the string is pulling in on the mass, it's hanging from one end, and it's also pulling on the ring. Now for a static case, where this isn't going to be rolling around, those two forces will have to be equal. So for example, if I have two people pulling on my arms, but I want to be stationary in the middle, these two forces have to be the same amount if they're in opposite directions. That's what we have here. So the force the string is pulling on the ring must be equal and opposite to the force that the string is pulling on the mass, and the force the string is pulling on the mass is that mass converted to kilograms times acceleration due to Earth's gravity. So that if this is 120 grams, that would be 0.120 kilograms, and then we can multiply by 9.8 meters per second squared, and we get so many newtons. But we're going to save the conversion to newtons. Alright, so now what I have is that lone mass is exerting a force on the ring. The ring's pulled in the direction of the masses, but there's a thing in the middle that stops the ring from falling off. In this example, we're going to have force A as 120 grams in the direction 56 degrees. And force B is going to be 80 grams. And the orientation of 324 degrees. Okay, so force A is heading out in this direction, so between 0 and 90. And force B, 324 degrees, more than 270, less than 360. Okay, so somewhere out there. And we're interested in what is the vector sum of these two. Okay, so the 120 grams that I've symboled here, that has to pull in the direction 56 degrees. Now, before I start, we've got orientations on these force tables. Some of these force tables have two sets of numbers. Let's see if I can show you this one. Yeah, I think you can see that. So two sets of numbers. Now notice on my diagram, my graph diagram, the orientations are increasing counterclockwise. So you look at this force table, you see set of numbers increases counterclockwise, set of numbers increases clockwise. Technically, those clockwise orientations are negative orientations, or you could think of them as compass directions, but we are not using the navigational definition here. So, we can think of the set that's increasing clockwise as negative orientations. Most of these force tables only have one set of numbers though, and those will be the positive orientations, as defined here. Okay. So I'm looking at the numbers that increase counterclockwise, and I'm going to find 56 degrees. That would be over here. And this pulley, these are actually called super pulleys because they're very low friction and very low mass. Now, when I was talking about the string tension being equal at the ring and also where the mass is hanging, that's only true if the string tension is exactly transferred by the pulley. That only happens for pulleys of zero friction and zero mass, so never. But these pulleys have very low friction and very low mass, so it's a very good approximation. And the center of the pulley has a little notch there. A notch there. That's what I'm lining up with 56 degrees. Also, they're super in the sense of being very low friction, very low mass, but not super strong. So this screw here that I'm tightening up on the bottom, it's very easy to over tighten that and actually break the pulley. So, very loose finger tight, not even regular finger tight, just very loose finger tight. In fact, that screw is only going to stop it from going left or right or horizontally. And once you have tension in the string, it really doesn't want to go horizontally. The string prevents that anyway. So just loose finger tight. So there I have 120 grams at 56 degrees. And now I'm going to put 80 grams at 324 degrees. Okay. 324 degrees is over here. So 80 grams, 50 plus 20 plus 10, and there we go. So now I have two forces simultaneously pulling on the ring. And the ring's wanting to go that way and that way at the same time. And what we're interested in is, what's the overall effect of those two forces? Well, the force table, this is important to realize, the force table does not directly give you the answer that we're after. The force table gives you something called the balancing force. Okay, let me bring this closer so you can see what I'm doing here. So here are the two forces that are pulling on the ring. And the ring is being pulled that way. So the vector sum of these two forces is some force that way. Like I said, the force table doesn't directly give us that answer, but it gives us something called the balancing force. If I pull a third string, or an additional string, in a certain direction by a certain amount, I can get this ring to levitate in the middle of the table. So the goal here is to get that ring levitating in the middle of the table. If the ring is levitating, the sum of all the forces acting on it add up to 0. Okay, so what we can do is pull on the ring and figure out what direction we need to pull in. I can see it's around that 200-degree orientation to balance it. And there is only one orientation combined with one force that will balance this. So do that. And then, through trial and error, I'm going to figure out how much force that needs to be. So, is 50 grams. That's not enough. But another 50 is 100. And that's not enough. Another 50. 150. Oh, too much. How about 140? 120, not enough. 140, getting close. You don't want these to swing, it does change the physics. Now about a couple more. 142. One more. 143. There's another 144. That looks pretty good. And once you think you've got it approximately balanced, there is a fine-tuning process that's important to do. For this to be technically to be perfectly balanced, these three strings should all be coming from the same point, which will be the center of the table. So what you want to do is you want to look down each string, and you should, if it's perfectly balanced, you should see the knot right in front of that center post. If the knot isn't in front of the center post, how do you fix it? Well, you can slide the knot. What does that do? generally, it often makes things worse. So slide the knot. Let's look at another one. Well, that one actually looks okay. This one over here, that's gotten worse. So let me try sliding that knot. And that's making it even worse. The ring is now off center. So here is my balancing force over here. Obviously it's not quite right. So I'm going to shift the orientation. See if I can get the ring centered better. And that looks pretty good. And you may need to adjust the amount of balancing force as well. But this looks pretty good now. So I can see that the knots are lined up with the center of that post in all three cases. And so in the experiment, I can write down what my balancing force was. And like I said, I put 144 grams there, and what is the orientation? Oh, it's to the nearest degree, 203 degrees. On the force table, you really don't need to worry about fractions of degrees. In fact, it's really, for typical cases, it's accurate to say within a couple of degrees. So I'll put 203 degrees. All right, so I found that the balancing force, it's not a 144 grams. And typically this is accurate to within a few grams, maybe 5 grams, say. So within 5 grams, and the orientation is usually within a couple of degrees, but it depends on the exact case you're looking at. So 203 degrees. All right. So I found the balancing force with the force table. Now, I can easily go from that to the vector sum of A and B. There's a simple arithmetic that needs to be done, but I want to explain why we need to do that. Okay, so to make this clearer, what I'm going to do is I'm going to color code these vectors. So A is going to be green, and then B is blue. In the graphical method, what we have to do is come up with a scale. For this particular experiment, in the graph paper, you have 1 centimeter representing 20 grams is a good scale. That's the scale on which you use. So use 1 centimeter to represent 20 grams. So that means that a vector of strength equivalent force 120 grams, well, that's 6 times 20 grams. So that's going to be 6 centimeters long. And that's in the direction of 56 degrees. So what you do here is, using the protractor, very carefully measure out the orientation, 56 degrees. That direction, and then draw a line 6 centimeters long. I'm going to exaggerate this. Six centimeters is tiny on this board. And I'm going to write a 6.0 0.00 centimeters, which you might think is ridiculously precise. We can't measure 100 centimeters, tens of millimeters with this thing with millimeter markings. But what I mean by that is try to get it bang on the millimeter mark, because you can't be too careful with this. And the same with the orientation. It rise 56.0 degrees. That means it's like right on the 56 degree mark. It's as careful as you can. You don't want to be sloppy with this, otherwise the little experimental uncertainties that go off on you. All right. Now the B vector, 80 grams at 324 degrees. All right. So that's this direction. Now the way we add vectors is we add a nose to tail. So I could draw the B vector in here, which I could do, but I'm not going to do. It's not as helpful as going up here. So we have the B vector starting with the A vector. So the axis of the B vector, actually like this. So B going in the orientation 324 degrees, which is somewhere between the positive x and negative 1. It's going to be here. So it's negative 1. And in fact, 324 degrees is 36 degrees short of 360. So the orientation to 324 degrees is 36 degrees below the positive x-axis. All right. So that's what I'm doing here. I'm measuring 36 degrees below the positive x-axis. That's the direction the B vector is going to hit. And then 80 grams. This scale, 20 grams per centimeter, divide this by 20, you get 4 centimeters. All right, I'm going to exaggerate it. Okay, so there, 4.00 centimeters as well as I can get it, and there's the 36 degrees as accurately as I can measure it, and notice how that's clockwise. That's technically a negative orientation. That's the same thing as a positive orientation of 324. There's the 324 degrees. Now, A plus B is from the beginning of A to the end of B. And in this experiment, we will sometimes add 2 vectors, sometimes add 3 vectors. When we add 3 vectors, we're going to naturally call them A, B, and C, so A plus B plus C. So for consistency, we're going to always call the vector sum D. So A plus B equals D. So D vector in there. And what I can do is measure the length, 7.2 centimeters. Let me write that in there. Let me write D here. .2 centimeters, and the orientation 20 degrees, maybe 21. So there's 21 degrees here. So 2 centimeters. Now clearly, the 21 degrees is not the 203 degrees. 7.2 centimeters isn't 144 grams, but 7.2 centimeters times 20 grams per centimeter, that actually equals 144 grams. All right, so that agrees. But the 21 degrees is not agreed with 203 degrees. Now, this is what's going on. The balancing force on the force table is exactly cancelling the sum of A plus B. So here I've got A and I got B. They're going this way, toward you. Well, A plus B must also be toward you. And in fact, it must be in the exact opposite direction as this balancing force, because the balancing force is cancelling A plus B. So D vector A plus B, it must be exactly opposite 144 grams to 3 degrees. Now with vectors, exactly opposite means the same amount but the opposite direction. So same amount, still 144 grams. Opposite direction means this way. And how do we do that numerically? Well, if we add or subtract 180 degrees. So, for example, if I take 21 degrees and I add 180 numerically, I get 201, pretty close to 203. I could subtract 180 and I'll get negative something. It'd also be in that same direction. Okay, so I add 180 degrees to this. Get 201 degrees. Now, remember I said treat the three methods independently. So basically, I'm going to barricade them off here. And I could get this result without having to graph and realize that. So how do I turn a balancing force into the vector sum without knowing anything about the graph, only using the force table? What I do is I add or subtract 180 degrees from this orientation. And it's completely optional whether you want to add or subtract. We generally don't like ridiculously high or ridiculously low answers. Okay, so obvious thing to do here would be subtract. So 203 degrees minus 180 degrees. So if I add, I get a crazy number. 4 grams, 203 minus 8 is 23 degrees. Okay, so that's what the force table says the vector sum is. So the procedure was I set up the A and B physical forces, I found the balancing force, 144, 203, and then I add or subtract 180 degrees from that balancing orientation. You can see how I did the graphing. So they're slightly different. The graphing is saying 144 grams at 21 degrees. Force table says the vector sum is 144 grams at 23 degrees. Now, if you're wondering, so what exactly is that 203 degrees? On the graph, so it's a balancing force. Well, the black vector there is the vector sum. Now the balancing force is exactly opposite. So there's the vector exactly opposite. And it's starting here. So the vector I just drew, its coordinate system is here. It is its x, and there it's y. It's heading in that direction. Okay? So for this red vector, there's 0 degrees, there's 90, there's 180, that's 270, right? It's a little more than 180, so you can see it's about 203. In fact, it'd be 201. So how does the mathematical method, the component addition method, using trigonometry relate to this? Well, we'll look at how it relates to the graphical method. So what I'm going to do is I'm going to remove all the numbers from the graph and replace it with symbols. So there's my A vector. Where my B vector was. We'll call this theta A. That's what we mean by the theta B. And we're trying to figure out D and theta D. So here is our D vector. And then in there is theta D. And we're going to do this completely mathematically. So the idea is this. You calculate the components of the A vector, x and y components. Now, the x component of the A vector is going to be this much. The y component of the A vector will be this much. The x component of the B vector is that much. It's how much these vectors go in the x direction. The y component of the B vector is that much, and it's heading that way. So By is that much. I'm going to write it over here. Now dx, right triangle for the D vector. Clearly it's x plus bx. It's dx. Now dy is this amount here. I can transfer over here. There's dy. Now, look at this really quick when you don't know any trigonometry. You can say, oh, looks like dy is ay minus by. However, by is negative. See how b is heading in the negative y direction? It's a negative component. And so dy is actually ay plus by. So dx is ax plus bx. And if I had a c vector, a third vector, I'd say plus cx. And dy is ay plus by. If I had a third vector c, I'd say plus c. In this case, you could say, well, cx and cy are both 0. So once we have dx and dy as numbers, and they could be positive or negative, then the idea is to calculate d and theta d. Now, using Pythagoras, the length of d is simply the square root of the sum of the squares. You've got a right triangle in there. Okay, so d squared would be dx squared plus dy squared. And so d is the square root of that. If we're just looking at this example here, this specific example, we know that theta, the tan of theta d would be dy, that side over dx. So that means theta d would be the inverse tan dy dx. Now, what you got to be careful with here is that only works if the d vector is in this quadrant or that quadrant, this inverse tan formula. It fails if d is hitting this one. So what does it mean for d to hit that way? Well, it means that the x component is negative, and it would mean that dx is negative. So it turns out that this equation works for as long as dx is greater than 0. By the way, it doesn't work at all if dx is exactly 0. Dx is exactly 0, the answer is going to either be straight up or straight down. You can't use the inverse tan. If dx is less than 0, so it's heading out this way, this equation gives you the wrong answer, but it's wrong by exactly 180 degrees. So there's an easy fix. So you just say, okay, theta d is, let's look at that calculation. We know it's exactly wrong. This is for dx negative. We know it's exactly wrong by 180 degrees, so we can fix it by adding or subtracting 180 degrees. All right, so the last thing is, how do we calculate these components? That's the one thing you got to be careful with. So here the trick is not with the magnitudes of the vector, it's the orientations, how to handle them. So I'm going to show you several cases for, let's just say the vectors have a magnitude of 1. Let's imagine a vector in the direction of 49 degrees, okay? 0, 90, 45 degrees. So if you calculate the cosine of 49 degrees, it turns out you get the x component. And if you calculate the sine, you get the y component. And to verify that that's true, you will notice that the y component is slightly larger than the x component, and they're both positive. This angle in here is 41 degrees. And what also works is, okay, so the x component, it's the cosine of 49 or the sine of 41, they're identical. The y component is the sine of 49 or the cosine of 41. So be very careful when you're calculating these components. You can define a vector in different ways. For example, 125 degrees, that orientation. Okay, so there's 90. 125 is another 35. About that direction. So we can define it as, okay, 125 degrees in there. We can say it's 35 degrees in there, or we can say it's, so that would be 35 degrees left of the plus y axis, or we could say it's 55 degrees above the negative x axis. 3 different ways to calculate x and y components here. The x component here is the cosine of 125 degrees, or it's minus the cosine of 55 degrees, or it's minus the sine of 35 degrees. 3 different ways to get it with the calculator. Just got to think very carefully about it. So you can, here's a way, form a right triangle. There's one there. There's another here. I remember it this way: cosine connected, sine separated. So the x component is fine. See how it's connected through the 55 degrees? That's cosine. See how it's separate from the 35? That's sine. And because it's going that way, left, it's negative. All right, let's look at another one. 205 degrees. So 205 degrees, it's more than 180, less than 270. In fact, 25 degrees more than 180. So it's going to be here, and that's going to be 25 degrees. There's the 205 degrees. And it can also be defined as 65 degrees. Say left with the negative y-axis or 25 degrees below the negative axis. So once again, there's three ways to calculate this. It turns out it's the x component is cosine of 205 degrees. All right. The x component is connected to the 25. And it's separate from the 65. So negative sine 65. Negative sine 65, negative cosine 25, or cosine 205 degrees would be the x component. And then the y component, turns out it's a sine of 205 degrees, or negative, y is negative in this case, negative sine 25 degrees, or so it's connected to the 65, or it's negative cosine 65 degrees. So let's suppose we have a vector going in the fourth quadrant. Let's say it's 49 degrees below the positive x-axis. So that's about that. Well, that's also 41 degrees from here. And technically that is a negative orientation. So I could write negative 49 degrees in there. And it's also technically this orientation, which is 270 plus 41. That's 311 degrees. Okay, so three different ways. For this case, the x component you can either get from the cosine of 311 or the cosine negative 49. And surprisingly, the cosine of negative 49 degrees is positive. X component is positive here. Or, so here's the x component. From this number here, you can see it is separate. So that's separate from the angle. So it would be sine 41. Sine of 41 degrees would also be the x component. The y component, it turns out the sine of 311 gives you the y component, which is negative. Or the sine of negative 49 degrees also gives you the y component. Or the y component is this, to that side, which is connected to 41 degrees. So negative the cosine of 41 degrees would also be y. So there are multiple ways to calculate these components. Be very careful with the sine. Be very careful with whether you're defining angle relative to the y-axis or the x-axis. Now, one of the reasons why these large orientations greater than 90 degrees are used, it's for writing algorithms in software. So instead of having lots of different options to calculating the components and keeping tracks of sines and things, it works out that the x component of A or B or C is always the magnitude. So in this case, it'd be like the number of grams times cosine of the orientation. So if I take the cosine, in this case of 311 degrees, or or even negative 49 degrees, numerically it's the same thing. It will give me the x component. And then the y component, I take the magnitude sine of the orientation. So the magnitude sine of 311 is the magnitude sine negative 49. That's what you got. Okay, so that's a recipe that always works. Defining orientations with respect to this. And you get the correct signs as well. When you go through the mathematical method, keep all of the signs. Here's the only place where the signs are going to completely disappear. You square negatives, they disappear. Okay, everywhere else, keep the signs all the way through, and you'll get the right